Hello all viewers, my name is Raimondo and I am a grade 12 calculus student, and today we will be looking at a question from Calculus Unit 2 on derivatives and specifically lesson 2.1 titled Derivative of a Polynomial Function. In the question we are given a polynomial and we will look to determine where the height is for certain values of t regarding time in seconds, as well as rates of change which can be determined by using the derivative of the function. So looking at the question, a flaming arrow is shot into the air to mark the beginning of a festival. Its height h in meters after t seconds can be modeled by the function h of t equals negative 4.9 t squared plus 24.5 t plus 2. A. Determine the height of the arrow at t equals 2 seconds. So A is a simple question that will not need anything we learned in calculus, but instead using our knowledge from functions. To determine the height, we will need to use the time that is given and plug that time in for t in the given polynomial to find the height at that time. In doing this, we can see that the height of the arrow is 31.4 meters when t equals 2 seconds. Now B asks us to determine the rate of change of the height of the arrow at 1 second, 2 seconds, 4 seconds, and 5 seconds. To determine the rate of change, the first thing we must do is take the first derivative of the polynomial. With the derivative, we will then be able to plug in the times that are given in the question into our new derivative equation and solve for each of the rates of change. For this polynomial, we will need to use our knowledge of the derivative rules to find the derivative of the polynomial. The ones that are specifically used for this polynomial will be the sum rule, power rule, and the constant rule, as there is a constant of positive 2 and there are powers on the values of t, and they are all being added to one another. When looking at the polynomial, we can separate it into 3 parts and find the derivative of each individually first. First, negative 4.9 t squared. We can use the power rule to find the derivative, which tells us to multiply negative 4.9 by n, which is the power, and in our case, 2. As well, to subtract the power by 1, so we are left with negative 9.8 t. Now, for the second part, which is 24.5 t, we can also use the power rule. We can think of t being to the power of 1. So by multiplying 24.5 by 1 and subtracting the power of 1 by 1, it gives us 0. And the t is no longer there. We are left with just a positive 24.5. Now the third part is the constant positive 2. As we know through the constant rule, the derivative of a constant is 0. Therefore, the derivative of the entire polynomial is negative 9.8t plus 24.5. To find the rates of change that are given in the question, we need to plug in each of the times to the given times to find the rate of change of the height at each of those times. Now looking at each of them, we can see that for some of the times the rate of change is positive and for some the rate of change is negative. The rate of change tells us how fast the arrow is traveling in meters per second and is traveling upward for the positive rates of change and downward when the rate of change is negative. Through using the first derivative equation for each of the times given in the question and plugging in times for t, we are able to find the correct rates of change. Now, C asks us what happens at 5 seconds. To see what happens at 5 seconds, we must, as we did for question A, use the original polynomial given and plug 5 in for t and see if we notice if something happens at this time to answer the question. In doing this, we can see that the t's cancel each other out when we use 5 as our t value, and we are left with just the constant 2 meters. This means that at 5 seconds, the arrow is at the initial launch height of 2 meters off the ground. For D, it asks us how long does it take the arrow to return to the ground. To find out how long it takes the arrow to return to the ground, we can make the height equal to 0 and solve for t. This will tell us when the height is 0, which is the height of the ground, and by solving for t, we will find out the time in which the arrow returns to the ground. In this question, we are given decimals, so it will be difficult to factor this out, and it will be much simpler if we just use the quadratic formula. By using the quadratic formula, we will get 2 answers, one positive and one negative. And we know in this question, the answer must be positive as we cannot go back in time and are looking for when the arrow returns to the ground. Through doing this, we find that the arrow will return to the ground when t equals 5.08 seconds. Now, E asks us how fast is the arrow traveling when it hits the ground. As we did for part B of the question, we must use the first derivative, which we have already found, and plug in the time when it hits the ground, which we just found in part D, to solve for how fast the arrow is traveling when it hits the ground. By using the first derivative and plugging in 5.08 for t, we can find that the arrow is traveling at negative 25.28 meters per second when it hits the ground. As you know, the arrow was shot into the air, and when it returns, it is descending to the ground, so it makes sense that the answer is a negative number. Now we can look at the graph of the function to confirm our answers for part A and C. For part A, we were asked what the height was when t equals 2 seconds, and we found that the height was 31.4 meters. Through looking at our graph, we can confirm that this answer is correct on the graph, as we can see that it is at 2 seconds, the height is indeed 31.4 meters. Through the graph, we can also confirm our answers for part C. We were asked what occurs at 5 seconds, and we were able to see that the height is 2 meters, which is the same as the initial height of where the arrow was launched. And our graph can confirm this. Now, looking at a career which we can use derivatives. Derivatives can be relevant in the real world when looking at the job of a quantitative analyst. Quantitative analysts are a small group of professionals in the financial industry who are experts in quantitative finance. They combine their knowledge of finance, maths, and computer programming and use this knowledge to develop complex financial models that are used by their employers to price and trade in financial instruments such as derivatives. Most models that they use come across underlying complex derivatives are the job of a quantitative analyst. On the sell side, such as investment banking, quantitative analysts are primarily involved with derivative pricing and risk management. In finance, they have a strong understanding of finance theory, financial markets, derivatives, risks, and risk mitigation tools. They require a strong hold on probability, statistics, linear algebra, differential, and integral calculus. For our question, we use a function that has to use the derivative to solve for different things. A quantitative analyst must use financial models and use the derivatives on a daily basis when looking at the future and trends. There are many other jobs that also will use derivatives on a daily basis. Thank you for listening.